Hey everybody, today comes from our Cognitive textbook, chapter 4.7. You'll have a reading assignment that goes along with this, and it's all about discrete random variables, or EQ. Why might expected value, or E of x, be useful? So what is a discrete random variable? Well, it's just a chance event that takes discrete values. So remember, discrete means countable, whereas we had these other things called continuous variables that were measurable. Discrete means countable. So I want to think about, let's let some event be the capital letter X, and I'll say that that event is going to be the number of heads that I get. Again, it's something that's countable in some chance process like a coin toss, but I'm going to do it 3 times in 3 coin tosses. So on its own, X can take any value from 0, 1, 2, or 3. That's what makes it a variable, because it can take varied amounts. Probability distribution is what shows all possible outcomes of an event and their respective probabilities. So the probability distribution is the thing that really makes these very, very useful. So what's a probability distribution look like? Well, a lot of times it's put into a table or maybe a histogram or something like that. We'll go ahead and look at it as a table. And I list out for X all of the possible outcomes that we can have, 0, 1, 2, or 3, and then I list out their respective probabilities. Now, I don't know what the probability of getting 0, 1, 2, or 3 heads is off the top of my head, so I have to actually list out the sample space U. What are all of the possibilities? Well, all the different ways that I can get 0 heads would just be 1, right? That's getting 3 tails. Okay, now what about getting 1 head? Well, the head can be the first toss, the head can be the second toss, or the head can be the third toss. And so this is what's known as, or we have 3 different outcomes here for that one, or 3 different outcomes for that one possible one. And then we can look at, what about getting 2 heads? Well, that's having the heads come first. The tail can be in between those 2 in the toss, or the tail can be the first in the 3 tosses. So that's all the different ways that we can have that happen. Or we can also have 3 heads, and that's pretty simple. Every one of them is heads. So now we look at how many different possible outcomes we have. We had 8. Only 1 of them resulted in getting 0 heads. 3 out of 8 resulted in 1 heads. 3 out of 8 resulted in 2 heads, and 1 out of 8 resulted in 1 heads. Now, an important note here is that your probabilities, the sum, is going to add up to 1. That's what we know about a sample space, is it's all possible events. It's that universal set. It's every possible thing. So our probabilities need to always add up to 1 whenever we are looking at a probability distribution. Now, why do we care about this, or how is it helpful? We like to calculate this thing called the expected value. So the expected value is the average outcome of a discrete random variable if you performed several trials of its chance event. So we denote this as E of x, or we also might call it mu sub x, because it's the average, right? Now, how do we calculate it? Well, it's actually a pretty simple formula. It's the sum of all of the outcomes, probabilities, times their respective values. And remember that summation notation is capital sigma. That's what the big E looking things looks like, and then P sub I times X sub I is their respective probabilities times their respective values of the outcomes, and to me that looks like Pixie. So I remember this formula pretty easily because it's the sigma Pixie formula. So what does that look like in this case? Okay, well, let's go ahead and calculate what's the average number of heads we would get if we toss a coin 3 times. If we did this many thousands of times, how often would we get, or how many heads would we get on average? Okay, so E of x in this case is going to be, we take the outcome of getting 0 heads, that value, and we multiply it by its respective probability. 0 times 1, 8. Well, the value of getting 1 heads is 1, and then we multiply that by its probability, 3/8. We have getting 2 heads, and that's by 3/8 probability, and then getting all 3 heads was just a 1/8 probability. Well, this is actually pretty simple for us to calculate now. We have 0, right? And then we have 3 times 1/8, or 3/8 times 1 is 3/8. 2 times 3/8 is 6/8. 3 times 1/8 is 3/8. adding all of that together, we get 12 over 8. But with expected value, we generally don't like to see fractions. We usually want to convert it to a decimal. It's just a lot easier for us to work with when we answer the next question. Okay, and so that in this case is going to be 1.5. And you might think, well, you can't possibly get 1.5 heads. Shouldn't I round? And you actually don't want to do that when we're looking at the expected value. Okay, expected value, we're okay with decimals, and we'll see why in a little bit. What does this tell you, though? This tells me how many heads I can expect to get if I were to do this many, many times on average. The average is the key part, right? This is an average over thousands and thousands of trials. I toss a coin 3 times. That means on any average one, I would expect to get 1.5. Okay? So that, again, doesn't seem to make sense. Let's take a look at a different example that might help it make a little more sense. Draw red from a standard playing card deck with 2 jokers included. Imagine this is a fun little gambling game. Somebody offers you a chance to play this game, and you have to pay $1 to play. So if you draw red, you receive $2. You won. Congratulations. But if you get anything else, you actually lose your dollar. What is the expected amount you win if you play this game many, many times? Well, it's a gambling game. It's a game of chance, so you want to know, what do you stand to lose? Okay? Let's see what would happen. Well, our probability distribution, we're going to have x being the amount 1. Let's go ahead and define that as our event, the amount 1. And x has a few different possibilities. We could have you getting a red, which means you will actually earn $1, okay? Because you had to pay your dollar, you're getting $2 back. That means you're in the plus. You got $1 extra. If you, however, get a black card, then you lose your dollar. You don't get anything back. Or if you get a joker, then you lose $1 as well. Well, what's the probability of each one of these? Well, there are 26 red cards in a standard deck and 26 black cards, and then there's 2 jokers, which means there's 54 total cards. 26 of them are red. Then we have 26 out of 54 that are black, and we have 2 out of 54 that are jokers. So the expected value, we would say you could possibly win $1 plus 1 times 26 out of 54, right? 26 out of 54 times you win $1, but then you have the possibility of getting a black, and that's losing $1 26 out of 54 times. You could also lose $1 by drawing the joker, which should happen 2 out of 54 times. When I add all of these together, it actually is very simple. We have 26 out of 54 minus 26 out of 54 minus 2 out of 54, and we end up losing out. These two, 26 out of 54s, cancel each other out. We have negative 2 out of 54, which is very simply the negative 0.0307, so on and so forth. And you might think, wait, I thought you said probability means you can't ever have anything that's negative. This is not a probability value. This is the expected amount you win. So what does that mean if you're expected to win negative amount? You're actually losing. How much are you losing? About 3 or 4 cents. Okay? Actually, I think it's negative 0.370 is the actual value. Negative 0.30370. So, on average, you lose 4 cents each play. And that might not seem like a big deal. But again, the idea is to do this thousands and thousands of times. So imagine the perspective of a casino. This is a very popular casino game, let's say, just for argument's sake. A casino offers this game to players and has about 350,000 plays per day. How much does the casino earn from this game on average? So now the casino is saying, the casino is the perspective that we are looking at, and we know then that the expected amount that the casino is going to win is going to actually be a positive 0.0370 cents, right? That's going to be our expected amount that the casino is going to win. But they're playing this game 350,000 times. Multiply those two together, and you're going to end up with $12,962 after we round to 2 decimal places. So the casino is going to earn, on average, $12,962 per day from $1 bets on this game alone. Good business to be in the casinos, right? Okay, so that's it for today's lecture. Remember, we talked about the discrete random variables, probability distributions, and expected values. Please make sure you read your Cognity assignment, work through the examples there, and then we'll be able to get started on our practice. Have a great day.